This is the Math 3 Unit 2 review. And number one, we have a graph of a piecewise function, and we're asked to state certain things about that. On part A, we have state the open interval or intervals on which f is increasing. So first of all, it's referring to f. I'm going to label this. This is our function f of x. And a function is increasing if you, or the graph of a function is increasing if, as you trace it from left to right, if it's growing. So I'm going to highlight the part that is increasing. Let's see, as I'm tracing from left to right, it's increasing. You don't want to go from right to left, only from left to right. So also when it's asking for the open interval, it's talking about the domain. So if I look at the x-axis, what matches up with those x values, we see it's the first point starts at 3 and goes over to 5. And so that's an open interval where it's increasing. There is another spot where it's increasing, this part right here. Right, so it's increasing here and it keeps increasing, so we also want to include that part of the interval. And those are the only those are the only places that are increasing, and they're connected. So we're going from 2 to 5. We're putting this in interval notation, and it says open. When you see that word open, you're just using parentheses. So we're parentheses 2, that's our starting point right here, comma, we're going all the way over to 5. Part B, state the open interval or intervals on which f is decreasing. So decreasing, as you trace your graph left to right, where's it falling? So it's decreasing right here, and it's decreasing over here. So parts of the domain, so that's from 1 to 2, and 5 to 9. So first interval, 1 to 2, so everything in between 1 and 2, even 1.1, 1.2, 1.3, and so on. And the other interval is going to be 5 to 9. Everything in between 5 and 9. Alright, part C, state the open interval or intervals on which f is constant. Constant means it's neither increasing nor decreasing as we move from left to right. And so we end up with a horizontal line during that part. So we see the domain of that part of the function is from -4 to 1. Okay. D, state the domain and the range of the function. The domain is a set of all x values for a function, so you're looking at the x-axis. You're looking at where that starting point is, and that's at -4, where the ending point is, and that's an x value of 9, and just checking to make sure there's no discontinuities in your graph. And this graph's fine, so we're everything in between -4 and 9 is included. Then you have to think about your endpoints. If your endpoints are open circles, you won't include them, but both these endpoints are colored in, and so we want to include them. So we use brackets. You always put the lowest value first, so go from left to right, -4 all the way to 9. Part E. We are asked to state the coordinates of any relative minimums of f. A relative minimum is a point where the graph changes from decreasing to increasing. And so 2 is a spot where that's a relative minimum, because as you trace the graph from left to right, it's decreasing, and then at that point it switches to increasing. Scanning the graph for some other places, I don't see any others. If you look at the last point that I'm highlighting, that's not a relative minimum, because we're decreasing, but it's not a changing point. There's nothing after that. We're not increasing after that. So don't include endpoints as relative mins or relative maxes, even if they look like they're the lowest or highest spots of your graph. So we got one relative min. The coordinate of that point is 2, 0. Okay, notice this is a coordinate, it's not an interval. It looks similar to interval notation, but it's not. It's a point. The point at when x is 2 and y is 0. For f, we're looking for a coordinate of any relative maximums. A relative maximum is where your graph changes from increasing to decreasing. So as you trace along, we're going constant, we're going decreasing to increasing, and then increasing to decreasing. So that point that I highlighted is a relative maximum. The coordinate of that point is 5, 3. And so 5, 3 is the only relative maximum on this graph, because it's the only spot that changes from increasing to decreasing. We have a couple true and false questions about our function. G says that f of 2 is greater than 0. Okay, so let's see what f of 2 is. F of 2 in our function, in our graph, is equal to 0. Because it's saying, hey, when you plug in 2 for x, what do you get for y? And if you go to the x-axis at 2, the point that's our relative minimum is at 2, 0. So now back to our statement. Well, f of 2 is equal to 0. That's saying f of 2 is greater than 0, so that's false. H says f of x equals 0. So our function y value, the y value is equal to 0 between x equals 1 and x equals 3. Okay. So when x is 1, there's our 1 right there on the x-axis. Here's our 3 on the x-axis. It is true that f of x equals 0 when x is 2. Right? That's the spot right here. And it's true that 2 is between 1 and 3. But this is stated a little weird. It says f of x equals 0. Does it mean at one point between 1 and 3, or everywhere between 1 and 3? So it's not as specific as it should be, and hopefully the test will be more specific than this. If not, I will clarify for you. So let's change this to f of x equals 0 between x equals 1 and x equals 3 for some, not all, but some x value. A little more specific now, and then so we can say that that's true, since f of 2 is equal to 0. Part I says f of 0 equals 1. Okay, well, f of 0, where's f of 0 on our graph? It's saying, okay, we're plugging in 0, we're plugging in 0 into our function, where the x value is 0. So here's 0 on the x-axis, and we're up here highlighting it. So we're really, that point is at 0, 2. So we can say f of 0 equals 2. They're saying f of 0 equals 1, and so we say false, since f of 0 is 2. Next one, f of negative 1.325 equals 2. Now that seems like a little silly statement there, but that value is on the x-axis. So they're saying if you plug in that value for x, you'll get 2 for y. So where is negative 1.325 roughly on the x-axis? Somewhere between negative 1 and negative 2. Let's say it's about right there. Okay. And so now look up at your function. Okay, there's my function value. So if x is negative 1.325, my y value at that point, you can see the height is 2. So that's a true statement. If I plug in negative 1.325, I do get a height of 2, or a y value of 2. Okay, it says f of x equals 0 2 times on the open interval from negative 3 to 3. Okay, so these are x values, from negative 3 to another x value, negative 3. That's interval notation. I'm going to mark those. So there's a negative 3 to 3. So if we're looking at our function from negative 3 to 3, I'll highlight that part. Okay, so if you're looking at the highlighted part, it's saying that that function equals 0. So the y value, or the height of that function, is at 0. So the height at 0, this right here that I circled, that relative minimum at 2, 0, that's a point where the function is equal to 0. But there's no other spot, anywhere where that function's coming down and hitting the x-axis and having a y value of 0. And so we have to say that this is false. If it said 1 time, we'd say true, but false. F of x equals 0 only 1 time. All right, number 2. Asks us to give an equation, given the equation, absolute value of x minus 3 is less than or equal to a, can we give a value for a that will give the following when we solve it? So first of all, we want a value for a that will give us no real solution. Okay. One thing we know is when we take the absolute value of anything, we get a positive answer, or we can get 0. Right? The absolute value of 0 is 0, but the absolute value of any other number is going to give you a positive answer. There's no way to get a negative answer. Okay. So if I have something like this, the absolute value of x minus 3 is less than or equal to negative 5. That's false, because the absolute value of x minus 3, I don't know what x is, but I know it has to be 0 or positive, and a 0 and a positive number can't be smaller than or equal to negative 5. So this is no solution, or no real solution. a, that's an n, equals negative 5. Don't have to put the quotations around a. I just did. I'll change it. Okay. Part B, we only want one real solution. When you're working with an absolute value, typically you always get two real solutions. The only time you get one real solution is when you have an absolute value that's equal to 0. And so if we have something like this, the absolute value of x minus 3 is less than or equal to 0, well, it can't be less than 0. So this is the same thing as the absolute value of x minus 3 is equal to 0. Because absolute value has to either be greater than 0 or equal to 0. And this is going to yield one solution. When an absolute value is equal to 0, only one solution. So this is true when a is equal to 0. If we want more than one solution, we just make sure the absolute value is greater than, or you just make sure a is greater than 0. So pick any number bigger than 0. 2 would work. So that's going to work. So let a equal 2. Three, solve for x. Show valid and appropriate work. I'm going to first add 3 to both sides of the equation and get 2 times x minus 3 squared. This is 0, so equals 6. Next, divide both sides by 2, and you get x minus 3 squared equals 3. Take the square root of both sides. When you do that, we end up with x minus 3 on the left-hand side and the square root of 3 on the right-hand side. But don't forget, when you take the square root, you need, it could be positive or it could be negative square root of 3. Lastly, add 3 to both sides, and we end up with x is positive 3 plus or minus the square root of 3. Part B, again, we're solving for x. In this case, the equation's somewhat split up on both sides of the equation. We're going to move everything over to one side. In this case, I'm going to move everything to the left side. So I'm going to add negative 5x to both sides and get x squared plus 5x plus 8 equals 2. And then I'm going to subtract 2 from both sides of the equation to get x squared plus 5x plus 6 equals 0. I'm going to try to solve this by factoring. I'm looking for two numbers that multiply to 6 and add to 5. 3 and 2 work. And so this factors to x plus 3 times x plus 2. Still equals 0. So if you have factors that are equal to 0, a product of factors that are equal to 0, then you can set each factor equal to 0 and solve. So we get two answers. X is equal to negative 3 and x is equal to negative 2. Part C, we have to, in this case, the equation is split up as well, and I'm going to move everything over again to the left-hand side. So I'm going to subtract 11x, so get 3x squared minus 11x equals 4. And then I'm going to subtract 4. So 3x squared minus 11x minus 4 equals 0. Here I'm going to try to factor again. When I factor here, there's a little bit more involved. I'm looking for two numbers that multiply to 3 times negative 4. So we got the 3 from the leading coefficient and the negative 4 from the constant. We multiply the first times the last. 3 times negative 4 is negative 12. So we want to come up with two numbers that multiply to negative 12 and at the same time add to the linear coefficient, the negative 11, the middle term right before the x. So two numbers multiply to negative 12, add to negative 11. What are they? I've got negative 12 and 1. So, since there is a number in front of x squared, we can't take the shortcut like we did in part B and go directly to factoring. Instead, we need to split these three terms up into four terms. That negative 11x gets split into that negative 12 and 1. So negative 12x plus 1x. When you add those, you still get negative 11x. We need to split them up in order to factor this. We still have the 3x squared up front, and we still have the minus 4 at the end. Now, in factoring, we're going to factor by grouping. We're going to look at the first two terms, ask what can we divide 3x squared and negative 12x by. 3x works. What's left is an x minus 4. Then look at the last two terms, the x minus 4. The biggest thing I can divide both of them by is a 1. And again, I'm left with an x minus 4. And for this to work, we want both of those parentheses to match. They both have an x minus 4. So because of that, we can factor out an x minus 4. And we're left with the 3x plus 1. Now it's factored. Take your factors, x minus 4 and 3x plus 1, and set them equal to 0, and solve for x. And there we have it. Number 4 through 7, we need to solve the following absolute value equations for x and graph the solution or solutions on a number line. If there's no solution, then we're going to write none and explain why. So number 4, we're going to first start by solving for the absolute value. That plus 1 is not part of the absolute value, so I'm going to subtract 1 from each side and get the absolute value of 2x minus 5 is equal to 11. At this point, we split this up into two parts. That 2x minus 5, when you take the absolute value of what number, what can give us 11? Well, the absolute value of 11 is 11, and the absolute value of negative 11. So that 2x minus 5 could be a positive 11, and that 2x minus 5 could also be a negative 11. Solving for x, we add 5 to both sides and divide by 2. So one of my solutions is x equals 8. On the second one, we add 5. Negative 11 plus 5 is 6. Negative 6. And then divide by 2 and get negative 3. When you graph the solution on the number line, you draw a number line, Locate 8 and negative 3. And just put a solid point at those two spots. Number 5, we want to get the absolute value sign alone on the left side of the equation. So that negative out front we do not want. To get rid of that negative sign, we can multiply both sides of the equation by negative 1. If you multiply the left side by negative 1, it becomes positive absolute value of x, 7x plus 7. And you multiply the right side by negative 1, you get negative 17. That's a problem because when you take the absolute value of anything, you should end up with either a positive answer or 0, never a negative answer. And so because of that negative 17, because you have an absolute value equal to a negative number, we're going to say no solution. Number 6, 2/5 times the absolute value of 2x plus 3 equals 20. That 2/5 is not part of the absolute value, so we are going to work on getting rid of that first. One way to do that is to multiply both sides of the equation by the denominator. If I multiply the right side by 5 and multiply the left side by 5, so right and left. On the left hand side, when you multiply that by 5, you're going to get 5 times 2 only. It only multiplies with the top part of that fraction, and then you're going to divide by 5. Well, 5 times 2 is 10. 10 divided by 5 is 2. So often people just cancel these 5's out and write that 2. So we got 2 times the absolute value of 2x plus 3 is equal to 20 times 5, which is 100. Then we can divide both sides by 2. And then split this up. So that 2x plus 3 could be positive 50, because when you take the absolute value of positive 50, you get 50. But that 2x plus 3 can also be a negative 50, because when you take the absolute value of a negative 50, you also end up with positive 50 as an answer. Solve both equations for x. So first one, 2x equals, subtract 3 and you get 47. So x is 47 over 2. And on the second equation, again subtract 3, 2x is equal to negative 53. Divide by 2, x is negative 53 over 2. When you graph that on a number line, it's nice to think of it as a decimal value. It's easier to find where it belongs. So 47 over 2 is going to be 23.5. And negative 53 over 2 is going to be negative 26.5. And so on our number line, say here's 0, 23 is out here, 24 is next to it. So 23.5 is going to be right in between 23 and 24. And then negative 26.5, well, we got a negative 26 somewhere to the left, and a negative 27 right next to it. We're going to go right in between those. For number 7, I'm going to start by dividing both sides by 3, and you get x over 4. The absolute value of x over 4 minus 6 is equal to 0 divided by 3, which is still 0. So that tells us that x over 4 minus 6 is equal to 0. That's the only That's what we have to take the absolute value of to get 0. That's the only possibility. When you have an absolute value sign equal to 0, that's the only time you're going to only have one equation to work with. Here we add 6 in solving for x, and then multiply by 4. And you get x is 24. Again, find a number line. Here's 0, 24 is somewhere to the right. Put a point there. 8 through 11, we are to solve the following absolute value inequalities for x and graph the solution or solutions on a number line. If there's no solution, again, we write none or no solution and some explanation to why. So in number 8, we are going to split up this into two problems. One is 3x minus 10 is less than or equal to 2. So I'm pretty much rewriting it, just dropping the absolute value sign. This sign that we're starting with is a less than or equal. If you have that less than sign, doesn't matter if you have an equal or not, but if you have a less than sign, it's what we refer to as an and problem. So I'm going to put the word and in between my two equations. The second equation, or inequality, is going to be 3x minus 10, switch your sign, greater than or equal to negative 2. So you turn the sign around and you change the sign of that last number. It's also good, before you even go that far, to just make sure everything makes sense. Can an absolute value be less than or equal to positive 2? Sure. Because an absolute value has to give you a positive answer or an answer of 0. If we had something like if we had a negative 2 instead, then we'd have an issue, because an absolute value can't be less than negative 2. It can't even be equal to negative 2. But here it's good to keep going. So now we're going to solve for x. Add 10. Divide by 3. And on the second equation we're going to add 10 again. And divide by 3. Um, 8/3 as a decimal is roughly 2.7. Okay, so between 2 and 3. So when we're sketching this, say here's 0, 1, 2, 3, 4. There's a point at 4. I'm going to color it in because it's got the equal sign. There's a point at 2.7, so roughly right here. Again, I'm going to color it in. And we have the word and. So it's going to be less than 4 and greater than 2.7. So when you have that and everything in between, you're just going to color in what's in between there, between those 2 points. 2.7 and 4. Number 9, we have negative 2/3. Absolute value of x plus 4 is less than 6. Here we want to get rid of that negative 2/3 first. So I'm going to multiply both sides by 3. And when I multiply the left-hand side by 3, and the right-hand side by 3. The left-hand side, we get 3 times 2 divided by 3. Well, 3 times 2 is 6. 6 divided by 3, we end up getting 2. And it's still negative. Absolute value of x plus 4 is less than 18. And then I'm going to divide both sides by negative 2. We get the absolute value of x plus 4 switch your sign when you divide by a negative. So it's greater than -9. Now, your absolute value, whenever you take the absolute value of anything, so the absolute value of x plus 4, no matter what x is going to either equal 0 or a positive number. So this expression here is saying, hey, when is this absolute value, for what values of x, will it be bigger than -9? The answer is always. This will always, no matter what value of x you get, 0 is always bigger than -9, a positive number is always bigger than -9, and that absolute value will always get you either 0 or positive. So in this case, there's no more work necessary. We can state that all real numbers is a solution. If we were to draw a number line, we just have to shade in the whole number line. I'm not going to do that on this one. Number 10. Subtract 4 first. And then divide by that 3. And you get the absolute value of 2x over 3 minus 1 is less than -2. Now think through this one before we split it up. Can an absolute value be less than a negative number? And the answer is no, because an absolute value is either equal to 0 or it's greater than 0. It's a positive number. And so there's no way you can get 0 or a positive number to be less than -2. And so there's no solution to number 10. Number 11. First I'm going to subtract 2 from both sides. So 2 times the absolute value of x minus 5 is greater than or equal to -2. And then I'm going to divide by 2 and get x minus 5, the absolute value of x minus 5 is greater than or equal to -1. Again, think through this problem here. When will an absolute value be greater than or equal to -1? Absolute value is either equal to 0 or it's a negative, or it's a positive value. So it will always be greater than -1. So again, we get all real numbers. Number 12. On this one, we have the graph of y equals f of x. And I'm going to highlight that. That's our line right here, or a line segment. And then we have the graph of g of x. That's this curve, and I'm highlighting in green. And we're asked a few questions about these. The first question is statement is to list all the labeled points that are solutions for g of x equals 0. Remember, this is really stating, okay, these are points where the y value of those points are equal to 0. That only happens on the x-axis. So another way to state these is to find all the x-intercepts of g of x. Well, g of x crosses the x-axis at point C, point G, and there's another point that is not labeled on there. Let's label it label I. Okay, so point I. B says list all of the labeled points that are solutions for g of x equals f of x. So this is asking, where are they crossing? And we could see that the two graphs are crossing at point D and at point F. C says to list all the labeled points that are solutions for y equals f of x. This is just saying, hey, list all the points on the line. So that's point E, D, H, and F. D asks us to list all the labeled points that are solutions for y equals g of x. So those are points on g of x. The labeled points on g of x. So that would be C, D, H, G, A, F, forgot I, and B. E asks to list all the labeled points on f of x that are solutions for g of x is greater than f of x. So in other words, g of x is above f of x. I'm going to highlight the spot where g of x is greater than f of x. And which function should I highlight? It says label all the points on f of x. So I can only highlight f of x, okay? So what part of f of x is g of x above f of x? So this is a part of f of x where the curve is above it. And this is a part of f of x over here where the curve is above it. Okay. So list all the labeled points on f of x that are solutions for g of x greater than f of x. So I don't see any points on where that's true, because point D and point H is when they're equal, and there's nothing in between them, and point F is where they're equal, and there's nothing to the right of that. So there are no points that satisfy that. Okay, on to number 13. 13 asks us to, tells us the table shows several points on two continuous functions, f of x and g of x. And so I'm going to graph what's given here. To graph f of x, I'm going to look at the first two rows. I'll highlight them in green. And I'm going to graph it in green. So when x is 0, y is 0. So 0, 0. When x is 1, y is 2. So 1, 2, 2, 4. And 3, 5. Okay. I don't know what it looks like in between these, but I do know that the curve goes somewhat through that. So maybe, I'm going to guess, maybe, I don't know, something like that. And who knows what happens after. Okay. Then in blue, I'm going to erase the highlighted here. And I'm going to highlight what I'm going to use to graph g of x. So those are the y values for g of x, and top row are the shared x values. Okay. So the first point I'll plot in blue is 0, negative 1. And then 1, 3. And then 2, 2. and then 3, negative 2. And so we somewhat connect these points. And I'm going to label, okay, this is g of x, and the green one is f of x. So let's take a quick look at what we have here. So we see that g of x and f of x are crossing somewhere between x equals 0 and x equals 1. We're not exactly sure where, but somewhere in between there, they have to cross. They also cross again somewhere between 1 and 2. I'm gonna just put a little highlight where they're crossing here, they cross here. And those are the only two spots we're seeing them crossing, and keep that in mind as we're answering some of these questions, okay? So A says on the number line below, shade the interval or intervals between the integers where the solutions to f of x equals g of x must exist. If no solutions must exist, explain why. So remember, when you're setting functions equal to each other, that's asking where are they crossing each other. Okay, and we're going to shade where we think they're crossing. So we kind of said that first shading is between 0 and 1 somewhere on the x-axis. So I'm going to say, well, shade between 0 and 1, saying somewhere in between there, that's where they cross. And then there's a second crossing between 1 and 2. So I'm going to shade again between 1 and 2. Maybe I should change the color here. Okay, saying there's a second one somewhere between 1 and 2. B, on the number line below, shade the interval or intervals between the integers where the solutions to g of x equals 0 must exist. So g of x equals 0, that's saying, hey, when is g going to cross the x-axis, or where are the x-intercepts of g? So let's take a quick look at that. G is the blue graph. Ignore the green graph. Where is that crossing the x-axis? Well, it's crossing the x-axis in two spots, somewhere between 0 and 1. And then there's another crossing over here. Okay, I'll show you, highlight the 2 points. Okay, somewhere between, well, it's 1, 2, so it's 2 and 3. So 0 and 1, and 2 and 3. So highlight between 0 and 1 and 2 and 3. Okay. And then part C, on the number line below, shade the intervals between the integers where the solutions to f of x equals 3 must exist. So what does it mean for f of x to equal 3? Okay, f of x is our green graph. And if I want f of x to equal 3, that means the y value of f of x is equal to 3. Well, on the y-axis, here's where 3 is. And I'm just going to put a little dotted line across there. So that's height 3. So it's really saying, hey, when is the green graph, that's f of x, when is it going to reach that height of 3? And that's going to happen somewhere on the x-axis, you know, if I trace it down, between 1 and 2. Right? You can see it reaching that height. Ignore the blue, focus on the green. That green is reaching that height of 3 somewhere between x equals 1 and x equals 2. So I'm going to shade between 1 and 2. Moving on to 14. 14 through 17, we're to graph the system of inequalities on the graph provided. Write the coordinates for one ordered pair that is in the solution set for the system and one that is not in the solution set. Okay. So I'm going to use some colors here. So first, graph that in blue. Y is less than or equal to 4. Well, if I just graphed y equals 4, 1, 2, 3, 4 on the y-axis, this line right here is y equals 4. But we also want it to be less than 4, so I'm going to shade below. And so the graph of the horizontal line and the shading together make y is less than or equal to 4. Now we have a second one. I'm going to graph in green. Y is greater than x. Now if we think about y equals x, that's the line. It's a parent graph. It goes through 0, 0. If you plug in 1 for x, you get 1 for y. And notice we don't want to graph y equals x. We want to graph y is greater than x. But I need to know the boundary line. So I'm not going to do a solid line. I'm going to dash it. Both directions. And we want to shade above this y equals x because it's y is greater than x. So I'm going to take the green and shade above. Okay. The solution to this is where the shadings intersect, where both colors are at the same time. And so I'm going to color that part in. It's hard to see it right now. Yellow, and I'm going to erase the blue and the green so you see what's left. Take that off, take that off. So that's the area where both shadings cross, and that's our solution. Now notice it says write the coordinates for one ordered pair in the solution set. So pick any point in that shaded region, or you can even pick a point on the solid line. Any of those would represent a solution. So I'll pick this point right here. There's no doubt that that's in the shaded region, so it's at -2, 1. There we go. Number 15. So 15, I'm going to graph the first one in green. That's our boundary line. It is going to be y equals 1/2 x plus 1 minus 2. That's a line. The parent graph here has been moved left 1 down 2 from 0, 0. So I'm going to go left 1 down 2 to get my first point. And I'm going to use the slope, the 1/2, to find my next point. So from the point I graphed, I'm going to go up 1, right 2 to get my second point. I'm not going to draw a solid line because it's not equal to this line. This is a boundary line. And it's greater than, so we're going to shade above. This time I'm not going to shade yet. I'm just going to maybe write the word above that line to know, okay, I'm going to erase that, but eventually I need to shade above that. I'm going to hold off on that. Okay, so the next one I'm going to graph in blue. I'm going to change the order of things here. This, I'm going to write it as the boundary line is y equals negative x squared plus 1. It's the same thing. I just swapped the 1 and the negative x. This is the boundary line that I want to graph with the equal sign. It's a quadratic. It's the parent graph has been moved up 1, so I'm going to put a point right here because the parent graph goes through 0, 0. I've moved up 1, and I need another point that this goes through. If I pick, let's say, 2, and I get y is negative 2 squared plus 1. Which is negative 3. So x is 2, y is negative 3. So 2 negative 3. And remember, this is a parabola, so it's opening down. And by the way, go back to the original that we highlighted. Notice it's y is less than. So I'm going to dash it. Not solid, and it's symmetric, so I'm going to match it on the right hand side. There's my upside down parabola, and its y is less than, so the shading is below, or we might say inside the parabola, because that's the below part. So we want to be above the green line, but inside or below the parabola. And so let me shade where that is. So this area here meets our criteria because it's above the green line but below or inside the parabola. So I'm going to erase the above and below here, so clean it up a little bit. Reshade that. Okay, so now what point is a solution? Here, we cannot pick a point on the parabola or on the line because those are dashed. We have to pick something we know for sure is in the shaded region. 0, 0 is the easy one. So 0, 0 is definitely a point inside our shaded region. Okay, number 16. Start with the top. Here it's less than or equal. So when we graph this, remember its absolute value gives us a V shape. We're going to use a solid graph here. So I'm going to graph y equals 1/3, absolute value of x plus 2. The parent graph of the absolute value is at 0, 0. That plus 2 is inside with the x, so that moves it to the left 2. So my first point is at negative 2, 0. And then find another value. I'm going to pick maybe x equals 1, because when I put a 1 in, I get 1 plus 2. That's 3, and 3 is a great number to multiply by 1/3. And so y equals 1/3 times the absolute value of 1 plus 2. Which ends up being 1, because you multiply the 3 with the 1, and you get 3 over 3, which is 1. So we plugged in a 1 and got a 1. And that's the right half of the V. Match the left half. Make it solid, because it's equal. And we are going to shade below. So I'm going to just write that here to know we're going to shade everything below. We'll get to the shading later. Next one in blue. Notice it's greater than or equal, so it's going to be solid again. and we're going to graph y equals negative absolute value of x. That's a parent graph, so it goes through 0, 0. If we plug in, say, x equals 1 into that, we're going to get y equals negative absolute value of 1, which is negative 1. So 1, negative 1 is a point we go through. That's the right half. Here's the left half. And it's greater than or equal, so we're going to shade above this. So below the green, above the blue, what does that look like? Well, that's going to be everything in here. And it climbs over here. Something like that. So anything on these graphs or in the shaded region will count as a solution. I'm going to pick something I know for sure. 0, 0 works because it's actually on a solid graph. But I'll pick something in the shaded region. Things safe right there. So negative 1, 2, 3, 4, down 1, so negative 4, negative 1. Number 17. Let's start with the top one, the exponential graph. Graph it in blue. I'm going to graph the y equals 2 to the power of x minus 2, but I'm going to make sure it's dashed because it's not really equal. And so the remember, the exponential function is a little different than the other functions. Its parent graph goes to the point 0, 1, not 0, 0. And so from 0, 1, I drop down 2, get my first point. Remember, there's that horizontal asymptote, which is 1 unit below that parent graph point. And let's get another value. If we plug in x equals 1, we get y equals 2 to the power of 1 minus 2, which is 0. And so we get this curve. Remember, it's dashed. Something like that. We're shading is greater than, so we're going to shade above it, not under it. The next graph, we're going to graph in green. That's going to be a line. I'm going to graph y equals negative 2 times x plus 1 plus 3. Again, it's going to be dashed because the original has a less than sign, no less than or equal. This is a line that the parent graph usually goes through 0, 0, but this plus 1 moves us left 1, and we're going to go up 3. So from 0, 0, go left 1, up 1, 2, 3, get our first point. And we need another point, so pick an x value, say 0. Then y is going to be negative 2 times 0 plus 1 plus 3. And you end up with positive 1, so 0, 1, dashed. And let me stop here because I graphed that point wrong. It should be at 0, 1, not 1, 1. There we go. Draw a dashed line through those 2 points. And we are going to shade below that line. Okay, so it's got to be above the blue, below the green. Where does that end up being? So that's above the blue, but below the green, right in here. Okay, and we can't pick for a solution is anything in that shaded region, but it's not going to be on any of the graphs because those are dashed. I'll pick something right dead center in there. Left 1, 2, 3, 4, up 2. So negative 4, 2 is a solution. And that's the end of the review.